Yo, hello, this is John Karan, and my student ID is MAT2509009 007. This is my presentation about quaternions and non-commutative systems. And this is my menu. Okay, chapter 1, the genesis of quaternions. On October 16th, 1843, the Irish mathematician William Rowan Hamilton carved a formula into Brockham Bridge in Dublin, which is I squared equals to j squared equals to k squared equals to I times j times k equals to -1. This was not just a set of symbols, it was an algebraic revolution. From that moment, mathematics was no longer bound by commutativity, and our understanding of the physics world gained a deeper language. What did he find? Hamilton was searching for a way to describe 3D rotations as elegantly as complex numbers describe 2D rotation. But he realized something profound. 3 dimensions were not enough. He needed a fourth. Thus, the quaternions was born. That way. Q equals to omega plus x times I plus y times j plus z times k. In this equation, omega is the scalar part and x times I plus y times j plus z times k is the vector part. Hamilton even saw this as a union of space and time. This, the scalar, as time and the vector as space. But the real breakthrough things in it was I times j equals to k, but j times I equals to minus k. Multiplication has no longer commutes. This was the first time in history that mathematics broke free from the commutative laws. And chapter 2, mathematical structure. Quaternions from a complete algebra system. There are 3. Multiplication is associative, but non-commutative. 2. Every non-zero quaternions has an inverse. 3. They form a division algebra, one of only 3 over the real numbers, alongside reals and complexes. The quaternion conjugate and the norm play key roles, similar to complex number, but extended into 4 dimensions. And there's also beautiful quaternions group as Q8 and 8 elements non-abelian group that captures the essence of quaternions multiplication. And there's a striking physical demonstration, the belt trick. It shows that in 3D space, a full rotation is not 360, but 820. A spiral property perfectly modeled by quaternions. And here is a chapter 3. About non-commutative systems. Hamilton's discovery opened the door to abstract algebra. Suddenly, mathematicians realized the algebraic system could be defined by axioms, not just as extensions of known numbers. Non-commutativity isn't just a mathematical trick. It's fundamental to physics. And look at this. In quantum In quantum mechanics, position and momentum do not commute like this. And 3D rotations are inherently non-commutative. Lie algebras, which describe symmetries in physics, are built on non-commutative brackets. Other non-commutative systems include matrix algebra and Clifford algebra, although I don't know what it is, showing how deeply non-commutativity is woven into mathematics and nature. Our next chapter, applications in 3D rotations. One of the most powerful applications of quantineers is in the representing 3D rotation. Traditional methods like Euler angles suffer from Jim-Bullock singularity, where 1 degree of freedom is lost. Quaternions solve this elegantly. A rotation by angle theta around the axis u is represented as this one. Applying this rotation to a vector v is done via conjugation, like this. Why the half angle? Because quaternions provides a 2 and 1 mapping to rotations q, and minus q represents the same rotation. This reflects the 4 pi periodicity of spinors. And the advantages include no Jim-Bullock computational efficiency, smooth interpolation via slurp, compact representation. And quaternions are used today in computer graphics, robotic, spacecraft control, like VR and AR, and molecular dynamics. And chapter 5, broader impact and broader mathematical impact. Quaternions are not just a useful tool, they're mathematically fundamental. The Frobenius theorem tells us that the only finite dimensional real division algebra are these three: R, C, and H, which represents real numbers like 1D, and complex numbers as 2D, and quaternions as 4D. This places quaternions in a unique and irreplaceable position in mathematics. They also inspired generalizations like this. In modern physics, quaternions appear in this. And in technology, quaternions appears in this three. Okay. From Hamilton's inscription on a bridge to guiding spacecraft and animating digital worlds, quaternions represents one of mathematics' most profound and practically abstractions. By daring to abandon commutativity, Hamilton not only founded abstract algebra but also gave us a language to describe the non-commutative nature of reality itself. As Lord Kelvin, who was wrong, said, Quantineers came from Hamilton after his really good work had been done. They have been an unmixed evil to those who have touched them. History, however, has proven him wonderfully wrong. And that's my presentation. Thank you.